Welcome back. We were discussing in the basic electrical and electronics engineering. The first topic that we have covered is on DC machines. Now, the next topic that we are going to take is on single phase transformers. The contents that we are going to cover in single phase transformers are basically the construction. We'll discuss the working principle, what is the EMF equation in a transformer, the transformation ratio, why the rating of a transformer is given in kilovolt ampere and not in kilowatt, what are the different losses associated with a transformer. We will discuss the ideal and the practical transformer, the phasor diagram of a transformer under no load condition and load condition. We will discuss the equivalent circuit, the voltage regulation in a transformer, the efficiency, and the two different tests, which are the open circuit test and short circuit test. This video lecture is divided into three different parts. In the first part, we will discuss from the construction to the rating of a transformer. In the second part, we are going to discuss from the losses to the phasor diagram of a transformer under load condition. And then we will discuss the equivalent circuit to the different testing of the transformer, that is the open circuit test and short circuit test. So lecture will be divided into three different parts. Let us see the introduction first in a single phase transformer. So a transformer is basically a static device. What is the meaning of static device? A static device is the one which is not having any rotating element. If we see the DC machine, there we have the rotating element, like we have the motors and the generators which are rotating. But in transformer, we don't have any rotating element. It is a static device. It can transfer the electrical energy from one circuit to the another circuit without the change of the frequency. So the frequency remains constant both at the input as well as the output. So whatever the input we are giving, the input frequency, whatever is there for the supply voltage, the same frequency we will get at the output voltage too. Now, since the transformer, there will be a change in the voltage. Either the voltage will be increased or the voltage will be decreased. Now, this is associated with the increase in voltage is associated with the decrease in the current. So it means that voltage and current are inversely proportional to each other, and vice versa. It means that if we decrease the voltage, the current will increase. The principle of the transformer operation is the mutual induction. So we have covered in the lecture series of self and mutual induction, where we have known that when the two inductors are there which are in close proximity to each other and they are coupled by mutual induction, then due to the current flowing in one of the coil, there will be voltage induced in the other coil, even though the two coils are not touching with each other. However, the two coils has to be in the close proximity. If the two coils are very far, then the mutual induction will not play any role. Hence, the principle of electrical energy transfer will not be there. It should be noted that in the transformer, we have to supply the AC voltage. That is, the voltage has to be time varying. If we are supplying a DC voltage, then the transformer winding will burn. So transformer do not operate under DC condition. Transformer operate under AC condition only. Now, when we talk about the application of the transformer, the major application lies in the transmission and distribution of electric power over a long distance through a wire, where the voltage is increased so that the losses associated with electric power decreases. Hence, when we require to transmit the voltage for a very long distance, we will increase the voltage through the transformer. Transformer application in electronic circuit is to step down the supply voltage to a level which is used by the low voltage circuit. Generally, in electronic circuit, the voltage requirement is very low. When we talk about the signal and the audio transformers, there are various coupling stages of the amplifiers, and to match such devices, microphones to the input of the amplifier, we required the transformers. Let us see the construction. So the transformer mainly consists of two coils. These two coils are basically the windings of the transformer, and they are placed on a common core. So the core is common between the two different windings which are present in the transformer. Now the transformer may vary in terms of their size, which is the capacity, the operating voltage, and it may also need other parts such as suitable tank, the bushing, the conservator, the breather, etc. So lot of different equipments are involved, or the devices are involved which form the part of a transformer depending upon its size and its operating voltage. However, from the first year point of view, the basic transformer course, we will discuss the two important parts, that is the core and the two different windings in the transformer. So the construction of the transformer, two basic parts, the core and the windings, will be covered in the first year lecture. If we talk about the transformer core, the composition of the material with which the core is made up of depends upon the voltage at which the transformer need to be operated, the associated current, and the frequency of the supply. The core materials are usually made up of soft iron and steel. Now, depending upon the use of the transformer, if the transformer has to be used at a very high frequency, which is above 20 kHz, then we prefer air core transformer. However, when the frequency is below 20 kHz, then in that case we prefer iron core transformer. Here the term iron just mean that we will be using the magnetic material whose permeability is high. If the permeability of the magnetic material is high, it will be easy to establish the flux in the core of the transformer. Now, the transformer is constructed by the laminated steel to produce a continuous magnetic path between the primary winding and the secondary winding. And the material that we use are basically high-grade silicon steel, because the hysteresis loss associated with the high-grade silicon steel is very low. So the core loss will be low. Since the supply that we are giving in the transformer is alternating in nature, this will lead the flux to be also alternating. It means that the flux is basically the function of time t, which will induce the eddy currents in the core of the transformer. The core of the transformer, when it is supplied with the voltage which is alternating in nature, the flux which is produced here in the core give rise to certain currents which are circulating currents in the core. These circulating currents are known as the eddy currents. The eddy current will lead to a loss which is known as the eddy current loss in the core material. Hence, the silicon content in the steel increase the resistivity to eddy current loss and thereby reducing the eddy current losses. So eddy current losses will be decreased when we are using the silicon content in the steel material. Usually, the transformer core is made up of CRGOS material. The meaning is cold rolled grain oriented silicon steel. So this is the material with which the core is made up of, which will reduce the eddy current losses. Further, if we need to reduce the eddy current losses, the core has to be laminated by a light coat of varnish by an oxide layer on the surface. So either we use oxide layer or we are using the coat of varnish. So this will again produce lamination in the core material. Now here two main shapes of the core is shown, one with a hollow core construction and another with a cell type construction. We can see that the core is laminated with a thin lamination. It is not solid. if we talk about the single lamination, this is what the single lamination look like, and so many laminations are there in this direction. And the core can be made up of E-type lamination or I-type lamination in case of cell-type construction. Now let us see the transformer windings. So we have understood the core. Now let us understand what are the windings present in the transformer. There will be two different coils which are present in the transformer. These are basically known as the windings of the transformer, and they are wrapped around a core. So the windings are wrapped around the core of the transformer. The first type of winding is known as the primary winding, to which the source of energy is fed. So whenever we see the winding of a transformer, if it is fed with the supply voltage, then it is known as the primary winding. Whereas if we talk about the second category of the transformer winding, which is the secondary winding, it is basically connected with the load. So if we talk about the other winding, which is connected with the load of the load ZL, that is the impedance of the load, then this winding is known as secondary winding. Now, if we combine both the windings, both winding has to be in close proximity, and there should be mutual induction between it with respect to the core. The first winding is connected to the supply voltage, which is known as the primary winding. The secondary winding is connected with the load. So these two windings are not physically connected with each other, they are mutually coupled. So whenever we are supplying alternating voltage as the supply, then due to the principle of mutual induction, we will be having the induced EMF in the secondary coil, and hence there will be a voltage induced across the load. When the load is present, then the current will start flowing in the secondary winding, and the primary winding will have the current I1 flowing. The windings are made up of insulated copper conductor. We know that the copper conductivity is very high. So we use such type of material for the windings whose conductivity are high, and this is insulated because so many turns form the winding. So each has to be insulated with respect to each other in the form of a round wire or strip. These conductors are present. So the conductors which are made up of copper are used for the windings which are insulated, and they are in the form of a round wires or strip. The windings are insulated from each other as well as the core using cylinders of insulating material. So different type of materials we are using for insulation. One material is known as the pressboard, other material is known as the bakelite. So these materials are used for the insulation of the winding with respect to each other as well as the core and the winding. Note here that for simplicity purpose of understanding, in the lecture we will take the primary winding and the secondary winding on two separate limbs of the core. So if we talk about the core material as the rectangular one, so we are taking the primary winding in one of the leg of the core and the secondary winding in another leg of the core, which is not so in case of the practical transformer. In practical transformer, usually the core is present first, and then there is a winding above which is the low voltage winding, and above which we are having the high voltage winding. So both low voltage and high voltage winding, which form the primary winding and the secondary winding of the transformer, they are present one above the another in a circular fashion with proper insulation between it, and they are not on the two separate legs of the transformer. This is only used for the simplicity purpose of understanding the concept of transformer. If such an arrangement, that is, if we put the windings on two separate limbs, what will happen? If we do that in actual practice, all the flux which is produced in the primary winding will not link in the secondary winding. Hence, there will be a leakage flux which is the flux flowing through the air through the core. So all the flux will not be present linking the primary winding and the secondary winding, and hence there will be poor performance of the transformer. The leakage flux will cause poor performance of the transformer. Hence we cannot put both the primary winding and the secondary winding on two different limbs of the transformer. To reduce this leakage flux, the windings are placed together on the same limb in the actual transformer. So this point, whatever we have discussed here, is only from theoretical point of view, not from the practical point of view. From the practical point of view, both the windings will be placed together on the same limb. Now here we see two different arrangement of the windings in the form of a core type transformer and cell type transformer. So here we can see the laminated core is there, which will be holding the flux, or the flux will be produced here. One of the winding, which is maybe the primary winding, the other winding may be the secondary winding. And if the winding is surrounding the core, that is known as core type transformer. In the other type of transformer, cell type, where the winding is surrounded by the core, means the majority portion is basically the core. Now this is quite a comparison of the core type and the cell type transformer. So in the core type transformer, we will see that there are two limbs and one magnetic frame, whereas in the cell type transformer we have three limbs and one magnetic frame. Since we have two limbs, single magnetic circuit will be formed in the core type transformer, but here the magnetic circuit will be two. Hence, in the core type transformer, the winding is encircling the core, whereas cell type, the core is encircling most part of the winding. Core type transformer, the windings are cylindrical in nature. The cell type windings are sandwich type of winding. Core type is easy to repair, cell type is not easy to repair. If we talk about the cooling aspect, we see that better cooling is provided in core type transformer because it is uniformly distributed on the two limbs. Ineffective cooling is there in the cell type transformer as windings are surrounded by the core. Application wise, low voltage transformer will use the core type transformer. Cell type is generally used in high voltage transformer. So this is the classification of two different types, that is the core type and cell type transformers. Now coming to the working principle of the transformer. So the transformer physical appearance, where we have the core, this is the core material is there, whose permeability is very high, and two different windings are there, the primary winding and the secondary winding. The primary winding is the one where the source is connected, and the secondary winding is the one where the load is connected. Now we are not talking about the low voltage winding or the high voltage winding. As of now, we are discussing the primary winding and the secondary winding. The primary winding can be the low voltage or the high voltage depending upon the requirement. Now here, these physical transformer is represented in the simple form of the equivalent circuit of the transformer, where two different coils are shown. The first coil, which is connected to the source, is the primary winding. The second coil, which is connected to the load, is known as the secondary winding. The primary coil can have N1 number of turns. The secondary coil can have N2 number of turns. And due to the supply voltage V1, there will be induced EMF E1 in the primary winding and the induced EMF in the secondary winding, and this will produce the voltage V2 across the load condition. You can see that two lines, straight lines are shown between the windings. So when two windings are there and two straight lines are shown in between it, this is the representation of the core. So if these lines are not there, it means it is air core transformer. If these lines are there, it means it is iron core transformer. Now when we are supplying the alternating voltage V1 in the primary winding of the transformer, it will draw a current I1 from the source. So the current I1 will start flowing in the primary winding. this current I1 will produce the induced EMF E1 in the primary winding as well as the flux in the core. So the flux is produced in the core. This flux is also alternating in nature. So phi is a function of time t. But if you see, this flux has to be constant. When we say constant flux, it means it is the RMS flux. So RMS flux, if we see, that is equal to the maximum value of the flux divided by the root 2 that will be there in the core. Due to this alternating flux, the EMF which is generated in the primary winding according to Faraday's law of electromagnetic induction is given by E1 is equal to minus N1 d phi by dt. Here, the negative sign indicates that in accordance with Lenz's law, the EMF will oppose the cause which is producing it. So the EMF E1 is produced because of V1, hence V1 and E1 will be antiphase with respect to each other. However, if we talk about the magnitude of E1, that will be equal to N1 d phi by dt. We will assume that the leakage flux is negligible and almost whole flux produced in the primary winding is linking the secondary winding. So whatever the flux is produced here, the entire flux is linking the secondary winding of the transformer. Similarly, if we talk about the magnitude of the induced EMF in the secondary winding, that is equal to magnitude of N2 d phi by dt. So the energy transfer is there from the primary network to the secondary winding of the transformer. Now here understand one thing, if you have the core of the transformer, on the left of the core, this is electrical energy, means we are supplying the voltage which will be taking the current, or in the extreme right we are also getting the electrical energy as it is connected with the load. But in between here the linking circuit is basically magnetic in nature because it is having a core material. So the energy transfer from the primary winding to the secondary winding is coupled through the magnetic network. Now the transformer can be the step-up transformer. What do you mean by step-up transformer? Is that when the secondary voltage is more than the primary voltage, then that is known as step-up transformer. It means that at the load we are getting more voltage than the supply voltage. This is only possible if the number of turns in the secondary winding is more than the number of turns in the primary winding. Whereas in the second category, which is known as the step-down transformer, where the secondary voltage is less than the primary voltage, it means we are decreasing the voltage. If we are decreasing the voltage, that is possible if the number of turns in the secondary winding is less than the number of turns in the primary winding. So step-up transformer will increase the voltage, whereas step-down transformer will decrease the voltage at the output. So one will be increasing and other will be decreasing. That will be the classification of step-up and step-down transformer. Now we will derive the EMF equation of the transformer, that is the electromotive force or the voltage equation. So in the primary winding, when you are supplying a sinusoidal alternating voltage, that will be resulting in the alternating current that is flowing in the winding of the primary. Hence, there will be a sinusoidal varying flux in the core. So the equation of the flux in the core of the transformer, we can write as phi is equal to phi m sin omega t, where phi m is the maximum value of the flux and omega is equal to 2 pi f, which is depending upon the frequency of the supply voltage. It means that the frequency remains the constant both at the input as well as the output and as well as the flux which is produced in the core. Now, the Faraday's law of electromagnetic induction E1 is minus N1 d phi by dt. So the differentiation d phi by dt we can obtain from the equation of phi as a function of time t. If we do that, then after certain step of the derivation taking d phi by dt, this is a function phi as a function of time t, we are getting this equation. If we observe in this equation, the value 2 pi f phi m and 1 is indicating the maximum value of the induced EMF. So maximum value of the induced EMF is equal to 2 pi f phi m and 1. Moreover, we can also see that the induced EMF E1 is 90 degree out of phase with respect to the flux phi. So when the flux phi is at 0 degree, the induced EMF we are getting at minus 90 degree. So flux and induced EMF are out of phase with each other with respect to each other at 90 degree. Now since in AC quantity we are interested in RMS value, that is the root mean square value. So capital E1, which is the induced EMF RMS, is given by the maximum value of the induced EMF divided by root 2. The maximum value of the induced EMF is 2 pi f phi m and 1 divided by root 2. We will get 4.44 frequency maximum value of the flux into N1. And it means that in the secondary coil we will get the same induced EMF, only the number of turns N2 we have to substitute in place of N1. Now hence we can remember that the induced EMF in the transformer equation, here I will write I to indicate that it is primary winding or the secondary winding, is equal to 4.44 frequency phi m, that is the maximum value of the flux, into number of turns Ni. So if I is equal to 1 in the primary winding, this will be 1. Now note here that this maximum value of the flux depends upon the flux density Bm and the area of the core with which the core material is made up of. So phi m is equal to Bm into area. When we will solve the numerical, we will see that mostly we will use this EMF equation where the maximum value of the flux has to be calculated in terms of the maximum value of the flux density and the area of the core. Hence, we have to note that if we divide E1 by N1 from the first equation and E2 by N2 from the second equation, we are getting a constant term 4.44 frequency into phi m. It means that EMF per turn is same in the primary winding as well as secondary winding. Now why we are saying this one to be a constant is the frequency of the supply is constant, which is the frequency of a particular country. In India we have 50 Hz, so the frequency is constant. Now if we talk about phi m, this is designed by the manufacturer. So the core material phi m value is also fixed, which is depending upon the maximum flux density Bm and the area of the core, which are fixed quantity. Hence we can say that the EMF per turn is basically same in the primary and secondary winding, which is a constant quantity. Also, since the primary and secondary winding are made up of various turns, so each turn will have the same equal EMF induced in the primary winding and the secondary winding. The next topic we are going to take is the transformation ratio. Now we have seen that the EMF equation E1 in the primary winding and EMF equation E2 in the secondary winding only depends upon the number of turns in the primary and secondary winding, otherwise the equation remains the same. Also we have seen that the ratio E2 by E1 is equal to N2 by N1 from the EMF per turn concept, which is equal to K. We have termed this one as the transformation ratio. So we have just arranged this one as E1 by N1 from the first equation is equal to E2 by N2 from the second equation. This is EMF per turn. So if I arrange this equation, I will get E1 by E2 is equal to N1 by N2. Now transformation ratio can be taken this one also, or it can be taken 1 by K. Different books take different ratios, otherwise the calculation will remain the same. Now if we neglect the losses in the transformer, so when we are supplying the voltage V1, the coil will have some resistance. This resistance, if we are neglecting it, and here the induced EMF, whatever we are getting E1, if we take V1 is equal to E1 when the resistance associated with the winding is neglected, then V1 is approximately equal to E1, V2 is approximately equal to E2. The transformation ratio E2 by E1 is equal to V2 by V1 is equal to N2 by N1 is equal to K. So this ratio is very important. We use it oftenly to solve the numerical. Now the power remains the same in the primary winding and the secondary winding. So this is the power. We know that power is the product of voltage into current. So V1 I1 is equal to V2 I2. If we arrange, we get I1 by I2 is equal to V2 by V1, which is again equal to the value of the K. So it means for the step-up transformer where N2 is more than N1, we will get K value, that is the transformation ratio, greater than 1. And the reverse process, that is the step-down transformer, N2 is less than N1, it means the K value is less than 1. And if we arrange this equation of the voltages and the current together, we will find one ratio proportion term where E2 by E1 is equal to V2 by V1 is equal to I1 by 2 is equal to N2 by N1. All will give you the transformation ratio K. Now note here that current and voltages are inversely proportional to each other. So whenever we are writing the equation, we have to write voltage inversely proportional to the current. So V2 by V1 will be equal to I1 by 2. This we are neglecting the losses into account. Now rating of a transformer. What is the meaning of a rating? Rating of a transformer indicates that how much output power can be produced in the transformer. So given the input power, what is the output power? So we know that the load in the transformer is not fixed and the power factor is continuously changing depending upon whether we are using inductive load or whether we are using capacitive load. So the rating is not expressed in terms of the power, that is in kilowatt, but in terms of the product of voltage into current. So we have seen in single phase AC network that the complex power on the apparent power is the product of voltage and the product of current, which is in the bigger quantity given by kVA rating of the machine. So the kVA rating is basically the rating on the transformer and it is not given in kilowatt. So whenever we are seeing the nameplate details of a transformer, we may see that it is given in the form of 20 MVA, and that is megavolt ampere, or we can say 100 kVA, 100 kilovolt ampere. Now this kVA rating of the transformer can be written as V1 I1, that is product of input voltage input current divided by 1000, because this is 10 to the power 3. Now since V1 I1, that is the input power, is equal to V2 I2 output power, and divided by 1000, we can get the kVA rating of the transformer. Now this equation is very important because from here we can calculate the full load current of the primary side. I1 is the full load current and I2 is the full load current in the secondary winding of the transformer. So kVA rating of the transformer will help us in obtaining the full load current in the primary and the secondary of the transformer. So when we need to find the full load current I1, that is equal to kVA rating multiplied with 1000 divided by V1, and when we need to find the full load current I2, that is equal to kVA rating multiplied with 1000 divided by V2. So these will help us in obtaining the full load primary and the secondary current. So this completes the first part of the transformer series which we are taking for the first year EEE course. In the coming lecture, we will discuss the losses, efficiency, equivalent network, and the testing of the transformer. So 2 more parts is remaining, and then we will discuss the tutorial problems and many problems we are going to take and discuss on this transformer concept. Thank you for now. See you in the next lecture.